In today's lesson, we learn about the Taylor and Maclaurin series. Taylor and Maclaurin can be used under single variable and two variables. So for each condition, there's a specific formula that we are going to use to solve problems. Then let us first look at the following formula. F of x, y is equal to f of x naught, y naught plus x minus x naught df dx plus y minus y naught df dy plus 1 over 2 factorial x minus x naught df dx plus y minus y naught df dx all squared. Then this formula can run up to 1 over n factorial x minus x naught df dx plus y minus y naught df dx. All this is up to n. So the following formula that we have here is called the Taylor series in two variables. So this formula is applicable when we have the point x naught and y naught not equal to 0 and 0. We can use the following formula to solve problem if we are given an equation with the points not equal to 0 and 0. So Taylor series with two variables, we use the following formula. Then how about then now when we have the point to be given as 0 and 0? If the points are 0 and 0, it means our x naught, this is called the x naught, and then this one is y naught. It means that where there's x naught now, we substitute with the value of 0 and 0. And then we'll have the following: f of x, y is given by, from the formula, it means we'll have f of x naught and y naught plus, we have said that x naught is a 0 this time around, then we will have x minus 0, and x minus 0 is x. So it means the formula this time around will be x df dx plus y minus y0, because y0 is a 0. Then we'll have y df dy, then plus 1 over 2 factorial, and then x naught is a 0, so we have x df dx plus y naught is a 0, then we'll have y df dy. This will be dy because we deal with y. There's a mistake here. Then dy, then all squared. So if we run this formula up to n, it means we'll have 1 over n factorial x df dx plus y df dy up to n, like that. Then when we look at the now this formula which we have here, it is no longer a Taylor series, but we can call it a Taylor series in the form of a Maclaurin, because the origin now is situated at point 0 and 0, or the point is now at the origin at 0 and 0. So we have formulated Maclaurin series with two variables. So if we're given the points x naught, y naught as 0 and 0, it means this is the formula that we are going to use. If the point x0 and y0 are given and they are not 0 and 0, it means you are going to use the following formula. Then how about then when we go into a single variable? If we focus on a single variable, everything that contains the variable y should be eliminated out of this equation. So which means now we'll have f of x given by f of x0. Y this time around should be eliminated because we focus on single variable, plus then x minus x0 df dx, plus we now focus on single variable, everything here should be eliminated. Then let us go into a second order, 1 over 2 factorial x minus x0 df dx. Then this part should be eliminated, and then when we eliminate this part, then we'll have everything squared like that, then up to n. So we have 1 over n factorial x minus x0 df dx. Then this part becomes 0, and then we raise everything to the n. Then now this formula is called the Taylor series with one variable. Provided that x0 is not equal to 0. So we use this formula. So if it happens that the value of x0 is given as 0, we are going to use the following formula. F of x might be equal to f of x0 plus x0 is a 0, so we will have x minus 0, which is x df dx, plus 1 over 2 factorial. x0 is given as 0, it means we'll have x df dx all squared, and then plus this formula can run up to n, so we'll have 1 over n factorial. We have said that x0 is a 0 this time around, it means we have x df dx everything raised to the n. And then now this formula is the Maclaurin series. This is the Maclaurin series provided that x0 is given as 0. So since now we have derived there some couples of equation and now understand that when we talk about Taylor series with two variables, we refer to this equation. Taylor series and single variable, we refer to the following equation. And the Maclaurin series in two variables, we refer to the following. And single variable, this is the equation that we use. And then now we can solve some examples. Let us look at the following example. Use the Taylor series of the function f of xy. So this is a two variable function. Then this function is x squared y plus 3y squared minus 2xy up to the second order. About the point 2 and 1. We want to use the Taylor series of the following function up to the second order about the point 2 and 1. So this time around, when we check the point given x0 and y0, it's not 0 and 0. So and it's a two variable function. So which means this is the following equation that we are going to use. So we'll have f of x naught y naught plus x minus x naught df dx plus y minus y naught df dy, and then plus this one is for the first order. Then let us go to the second order. The second order is 1 over 2 factorial x minus x naught df dx plus y minus y naught df dy, then all squared up to a second order. So this is the following formula that we are going to use to solve this problem. Now because of the square, then this formula need to be simplified before we can do some differentiations. So this is f of x squared, f of x naught y naught plus this part is already simplified, is fine. We have x minus x naught df dx plus y minus y naught df dy, then plus 1 over 2 factorial. Because of the square, then we have to remove the square. We multiply this expression by the same expression. Then when we multiply this expression by the same expression in the other bracket, we are going to get the following. Then it means we have x minus x naught squared because we multiply by the same base. Then we add the exponent, and also this part have to be squared. So it means we have second derivative of f with respect to x. So this must be dx squared plus, then when you take this part, you multiply by this part, you will get x minus x naught y minus y naught, then this part will multiply this part. What we will get is d squared f over dx squared. So because that, we are also going to multiply this side again back to this side, and according to the equality of mixed partial derivatives, when we differentiate f with respect to x, and again we differentiate it with respect to y, is the same as when we differentiate y with respect to x for the second time. Then it means here we must have 2, then plus y minus y naught should be multiplied by y minus y naught, and finally we will get y minus y naught squared. Then the derivative of f with respect to y should also be squared because we multiply by the same term, then dy squared. So this is all we need to know before we can solve this problem. Then now what we need is the following. We have to find f of x from this equation, and then we also have to find df dy from this equation, and then after finding df dy we can come and find d squared f over dx squared, and then the following, and then lastly we're going to find the following terms. So first let us find df dx. df dx, we differentiate this equation with respect to x. So when differentiate it with respect to x, we are going to get 2xy plus this treated as a constant, it's a 0. Then we differentiate this part with respect to x. So this will give me minus 2y. And then at the same time, we substitute the point 2 and 1. So it means df dx at the point 2 and 1 must give me 2x, and then x is a 2, y is a 1, minus 2, y is a 1. 2 multiplied by 2 is a 4, 4 minus 2 is a 2. Then these 2 will represent df dx. Now let us come to df dy. We differentiate our function with respect to y. When we differentiate this function with respect to y, we get x squared plus 6y minus 2x, which implies that when we substitute the point in this equation, the point 2 and 1, we are going to get, we have 2 squared plus 6, y is a 1, minus 2, x is a 2. This is nothing but equal to 2 squared. 2 squared is a 4. 4 minus 4 is a 0, which means we are going to have 6 like that. Then we also need to find this part, which is d squared f over dx squared. Then it means we differentiate f with respect to x twice this time around, but already we have differentiated f with respect to x, which is this part. Then let us differentiate this equation with respect to x. So when we differentiate this equation with respect to x, we get 2y. Then this one is a constant because it doesn't contain the variable x. It will give me a 0, which implies that then d squared f over dx squared at a point 2 and 1 will give me 2. The value of y is the 1. 2 times 1 is nothing but a 2. And then we also need to find this part. Where is this part? Yeah, this is a y squared, not x squared. Because we multiplied df dx, df dy, we must have dx dy like this. So now let us find the following: d squared f over dx dy. And then from this equation, we differentiate it this time around with respect to y. Then it means we are going to get 2x. This is 2x minus 2, which is equal to, or it implies that df squared dx dy at a point 2 and 1, we substitute the point in this equation. X is a 2, and then we'll have 4 minus 2, and 4 minus 2 is a 2. Now we have the following. We are sorted. We can come to the last term, which is our d squared f over dy squared. Then we differentiate y, or the function f with respect to y twice. We've already differentiated this function with respect to y, which is this equation. Now we differentiate it with respect to y again. Then we get 6, because when we differentiate with respect to y, this part doesn't contain the variable y, so it directly gives us a 0. Also this one will give us a 0. Then we differentiate 6y, we get 6. Then when we're at this point, we are just going to substitute the values directly into the equation, this one. So it means now we have f of x, y given by f of x naught and y naught. Then this one is nothing but we substitute the original point into the original equation. So we have x as 2, 2 squared is a 4, 4 times 1, because y is a 1, so we have a 4, plus 3, y is a 1, so 3 times 1 squared is a 1, we have a 3, minus 2, 2 times x is a 2, y is a 1. And then we have the following, which is 4 minus 4, and then the answer is a 3. So it means that for f of x naught and y naught, we have 3 plus We have 3 plus x minus x naught. We have x minus x naught. X naught is a 2, so which is x minus 2. Then df dx. What is df dx? We have said that df dx is a 2. Then we multiply by 2 plus y minus y naught. Y naught is a 1. This is a 1. Then df dy. What this one? df dy. We've said that df dy is nothing but a 6. So this is a 6 we get. Then now we are done with this part. Plus 1 over 2 factorial. 1 over 2 factorial is just the same as 1 over 2 times 1, so which is 1 over 2. Now we have the following. X minus x naught is a 2, then all squared. Then this part, the second derivative of f with respect to x, we have said that the answer is a 2, is this one. Then we multiply by a 2, and then plus 2, x minus x naught. X naught is a 2, y minus y naught. Y naught is a 1. And then we have the following, which we have to replace in terms of a value. So we've said that d squared f over dx dy is given by, we've said that the answer is a 2. Then we plug in 2 plus, we have y minus y naught. Y minus y naught. Y naught is a 1 all squared. And then this part here can be replaced by 6. We have 6 here. And then we write in 6. So when we're at this point, all we have to do is to simplify this expression. Now for the sake of space, let me rewrite what we have here in a new space. We have f of xy. We found 3 plus x minus 2 multiplied by 2 plus y minus 1 multiplied by 6 plus 1 over 2 x minus 2 all squared. This is multiplied by 2 plus 2 x minus 2 y minus 1. This is multiplied by 2 plus y minus 1 all squared. This is multiplied by 6. I did not change anything. What I've done, I just rewrote everything which we have here. And then let us now continue simplifying the following problem. We have 3 plus x minus 2 multiplied by 2. Then we can multiply the 2 inside the bracket. So we have 2x minus 2 times 2. We get 4 plus, we multiply the 6 inside the bracket. Then we get 6y minus 6 multiplied by negative 1. We get negative 6. And then plus 1 over 2 x minus 2 all squared. This is the same as x times x, and x times x is x squared. And then x multiplied by minus 2. So this will give me a minus 4x. And then minus 2 multiplied by minus 2, it's a 4. So all this is multiplied by 2 plus 2. X multiplied by y is xy. x multiplied by -1 is negative x, minus 2 multiplied by minus y is minus 2y, minus 2 multiplied by minus 1 is a plus 2, and then everything should multiply the 2 outside the bracket. So now when we check, we have y minus 1 all squared. So this is the same as y times y. Y times y is y squared. Y multiplied by minus 1, we get minus y like that, minus y times minus y, so we'll get minus 2y in short. But let me just write this down so that you can understand. Then minus 1 multiplied by minus 1, we get positive 1. Everything should be multiplied by 6. And then let us continue. We have 3 plus 2x minus 4 plus 6y minus 6 plus, now let us put this half inside the bracket, then we'll put it inside the bracket, then this 2 will cancel 2 for this expression, then we will have the following: x squared minus 4x plus 4, and then we multiply this half inside the bracket again, then this 2 will cancel the following 2, and then we'll be left with only 1. Then we have plus 2xy minus x minus 2y plus 2 plus, then when we multiply this half inside the bracket, we'll have half multiplied by 6, which is 3, and then 3y squared minus 2y plus 1. And finally, we can also multiply this 2 inside and then this 3 inside. We have 3 plus 2x minus 4 plus 6y minus 6 plus x squared minus 4x plus 4 plus, we multiply the 2 inside, we get 2xy minus 2x minus 4y multiplied 2 by 2, we will get a 4 like that, plus multiply the 3 inside, this is 3y squared minus 6y, when you multiply 3 by 2y, 3 multiplied by y by 1 is a 3. Yeah, so now we can add the like terms where possible. So let us check. We have 3 here, we have 3 plus 3 plus 3 is a 6, so 6 minus 6 is a 0, and then the 3 are gone for now. We have minus 4 plus 4, so they give us a 0, we forget about them. What else do we have? We have 2x minus 2x, they give us a 0, we forget about them. And then what else do we have? We have 6y minus 6y, they also give us a 0 and we forget about them. What else? Let us check. And then we have x squared remain, and then the 4 and this 4 will remain, so we'll have 4 plus x squared. We have the following minus 4x, yeah, minus 4x, then we can check what else do we have. Minus 4x, 2xy, we have plus 2xy, and then minus 4y, we have minus 4y, yeah, so minus 4y, what else? 3y squared, so plus 3y squared. Then this is our final answer for this problem. Then we can also look at one more problem for the sake of practice. For the sake of practice, let us check the following problem. We want to use the Taylor series of the following function f of x, y, given by e to the x sine y. So at a point, this time around, our point is 0 and 0. So the same formula applies. When we check, it's a two-variable equation, but this time around, our x naught is a 0 and our y naught is also a 0. Remember, we have said that f of x, y is given by f of x naught, y naught plus x minus x naught df dx plus y minus y naught df dx, then close bracket, plus up to second order 1 over 2 factorial. Then we have x minus x naught df dx plus y minus y naught df dy. I mean, this will be dy. I probably make some mistakes. You need to be extra careful when dealing with the Taylor series and stuff. So this will be all squared for second order. But take note, x naught is a 0 and y naught is a 0. It follows that, so we have the following equation, x naught, y naught plus. If this is a 0, it means we'll have x and then df dx plus y naught is a 0, we have y df dy plus 1 over 2 factorial. X naught is a 0, it means now we have x df dx plus y naught is a 0, y df dy, and then all squared. And then now, because of the square, so this formula can be simplified as follows. We must have f of x naught, y naught plus x df dx plus y df dy plus 1 over 2 factorial 1 over 2 factorial. Because of the square, then we're going to multiply x by x, which will lead us to x squared d squared f over dx squared, like that, then plus 2xy d squared f over dx dy plus, then we multiply this term by the same term, we must get y squared df d squared f dy squared. So this is all we need to do for this problem. And then from now on, what we have to do is to differentiate our function. This is our function first with respect to f, with respect to x, and then second we differentiate the function with respect to y, and then we come to this term, and lastly this one. So let us go and do as such. But now for the sake of specs, let me do the following. I'll rewrite our equation because it's very important. We need it at this moment. I'll write the following equation, f of xy. We've said that we found f of x naught, y naught plus x df dx plus y df dy plus 1 over 2 factorial x squared d squared f over dx squared plus y squared d squared f over dy squared. And then we'll also need the equation f of xy. We have said that the equation is given by e to the power x sine y at the point 0 and 0. Then what we need to do now is to differentiate this equation with respect to x. So let us differentiate this equation with respect to x. Then df dx. When we differentiate with respect to x, this is a natural log e. Then with respect to x, then it doesn't change, it remains the same. So look at e to the x sine y, which implies that df dx at the point 0 and 0 now we'll have e to the power 0, the sine of 0, because y is a 0, and we get e to the power 0 is a 1, sine 0 is a 0, and then 1 multiplied by 0 we get a 0. And then we'll also need df dy. Let us differentiate the function this time around with respect to y. When we differentiate this function with respect to y, it means we're going to keep e to the x neutral, and then we differentiate sin y. The derivative of sin y is cos y, so it means we'll have e to the x cos y, which implies that df dy at a point 0 and 0, we get e to the x. So x is a 0, e to the 0, the cosine of a 0. E to the 0 is a 1, multiply the cosine of a 0 is also a 1. Then we get 1 like this. So what else do we need? We found df dx, df dy. Now we need this part. We differentiate f with respect to x now for the second time. D squared f and dx squared. This is nothing but this is our first derivative of the function f with respect to x. We differentiate it again with respect to x, so it doesn't change. The natural log e to the x, it remains the same, sin y. And then by substituting the same values of 0 and 0, so we get e to the 0, the sine of 0. Sine of 0 is a 0. 0 times 1, we get 0. Then we are done with this one. Now we are here, we differentiate that part. All right, now we are here. So take note that when I was rewriting this equation, I left the middle term, the term that contains 2xy d squared f over dx dy. This term should be included in this equation. I left it when I was rewriting this equation. So, but we need to include it when we solve this problem. So now let us focus on d squared f over dx dy because it is part of the equation. So we go to our function f, the first derivative of the function f, but this time around we differentiate it with respect to y. So it means we will get, when we differentiate this part with respect to y, e to the x remain, then sin y, the derivative of sin is a cos, which implies that second derivative of f with respect to x dy at a point 0 and 0, when we substitute 0 where there is x, we get this, the cos of 0. E to the 0 is a 1. Cos of 0 is also a 1, which means we have the following as our answer. And then we can now find this part, d squared f over dy squared. So the first derivative of the function f with respect to y is this one. Differentiate this function with respect to y. So we keep e to the x as our constant. The derivative of x, we get nothing but a negative sign. So we can put negative this side, the sign of a y, which implies that the second derivative of the function f with respect to y at a point 0 and 0 can be substituted as follows. So negative e to the 0, the sign of a y. So the point is that the sign of 0 is a 0, so everything becomes 0. From now we can substitute these values into our equation. So f of xy is nothing but f of x naught y naught. This one is found by substituting the point from the original equation. So we have f of x naught y naught into the original equation. This is our original equation. So e to the 0, the sign of a 0. The sign of 0 is a 0. Then we get this. So it means we have this point is a 0 plus x. We multiply by df dx. We have said that df dx is a 0. Then plus y multiply by df dy. Df dy, we found 1, so it's y times 1. Then plus 1 over 2 factorial. Then x squared, we multiply by second derivative of the function f with respect to x. We found 0, so we multiply this part by 0 plus y squared. Then the second derivative of the function, this part. So this bracket actually should be covering everything, yeah. So y squared, second derivative of the function y with respect to f with respect to y is a 0, and then plus 2xy. So second derivative of function f with respect to x, but this time around differentiated with respect to y. It is this part. We found 1. Now let us simplify and see what we get. We have a 0, x times 0 is a 0, y times 1 is just the y, plus 1 over 2. 2 factorial is 2 times 1. Then inside the bracket, x squared times 0 is a 0. Then we get the following. Y squared times 0 is a 0. So it means what we get is nothing but 2xy, like this. And then we have y plus, then multiply the half inside, we get xy. Yeah, we multiply the half inside, 2 will cancel 2, and the xy will remain. So you can take y if you like, and then you have the following. So this is our final answer that we get when we reduce our Taylor series at a point 0 and 0. Then thank you for watching this video. If this video was very useful, don't forget to subscribe to the channel and like it. Thank you.